Okay, in the predator-prey model, we had this matrix came up. The matrix with columns 4, 1, and -2, 1. And then I gave these vectors, pulled them out of thin air, 10, 10, and 2010. And it turned out, if you compute these, that AV is 2V and AW is 3W. And these are the eigenvectors and eigenvalues, right? V is an eigenvector with eigenvalue 2. W is an eigenvector with eigenvalue 3. But the question is, where did I find V and W? I pulled them out of thin air. And we didn't know that the multiplying factors would be 2 and 3, right? So I want to try to explore this for a moment. So in general, we're looking for equations of the form ax equals lambda times x is the kind of way people tend to write this. So we want, i.e. we want to find a non-zero vector x. This is going to be important that it's non-zero, because certainly if x was 0, then this becomes kind of trivial, right? So non-zero x equals 0 would satisfy that for any lambda. So I'll just put that over here. We definitely don't want x to be 0. And lambda is a real number, right? Which could be 0. Nothing that says that couldn't be 0. We want to find a non-zero vector x. Let me even write that. Non-zero vector x and a real number lambda satisfying this equation. That's the goal, right? And so naively, if we didn't know about V and W and 2 and 3, how would we find these? So let's actually write this out. So let's actually write it out as like 4 minus 2, 1, 1 times some vector x1, x2 is lambda times x1, x2. But that's really lambda x1, lambda x2, right? Again, I want to be super naive about this. If we just write this out, this is a system of equations, right? This becomes 4x1 minus 2x2 equals lambda x1, and x1 plus x2 equals lambda x2. The problem is, first off, okay, these aren't constants after the equal sign, right? x1 and x2 are actually after the equal sign. That's already a little bit weird. But the thing I want to say is that this is like two equations. But how many unknowns do we have? We have actually 3 unknowns. We don't just have x1, x2. We actually have lambda is unknown. And that looks really daunting and bad at first. We're like, how the hell are we going to find this? How are we going to find lambda x1 and x2 when we only have 2 equations? But here's the saving grace. Like, we can rewrite this as a system of equations in the more standardized way, right? So if we actually subtract the lambda x1 and the lambda x2 to the left side, right, we actually get 4 minus lambda times x1 minus 2x2 equals 0. And x1 plus 1 minus lambda x2 equals 0. I just rearrange the equations. And what we want, so now that, notice this really is a homogeneous system. We have zeros after the equal sign. There actually aren't any non-zero constants here. And x1, x2 are not should not both be 0. So in fact, we want non-zero x so in other words, we want a non-trivial solution to this system. We want there to exist. Remember, the x1 and x2 equals 0 automatically is a solution always to a homogeneous system. But we want, if we're trying to find, lambda x1, x2 to satisfy this equation, we're looking for a non-zero vector x. We want there to exist a non-trivial solutions to this homogeneous system. But there's a nice way to do that, right? Or there's a nice way to tell whether or not there exist non-trivial solutions. If there's non-trivial solutions, right, that implies the presence of a free variable. We should have known that now. And that implies that there's not a pivot in every column or row, because this is a 2x2 system. And that implies that our matrix is not invertible. But I have to be really careful. What matrix do I mean? What matrix? I don't mean A. In fact, our matrix that we started with, A, is invertible. It's the columns linearly independent. You can check. Not A. In fact, if we look at this system and rewrite it as maybe an augmented system or a matrix times vector, this is really 4 minus lambda minus 2. Oh my God, I hope my 2's and my lambdas don't look too similar. I'll try to draw them carefully so they're not. That's a lambda. That's a 2. Okay. 1 minus lambda. Right, this is what we have when we rewrote this. And so we want this matrix to be non-invertible. We want this to be non-invertible. But we have a way to check if a matrix is invertible or not. We could just take its determinant to see if it's 0. And this is beautiful because it gets rid of x1 and x2. Right, before we were dealing with these 3 unknowns, lambda, x1, and x2. But really what we're looking for is just a lambda that makes this, when we subtract the lambdas off the diagonals here, that off the diagonal here, that makes this matrix non-invertible. So, by the way, what do we call this matrix? There's a nice way, this matrix is a nice way to rewrite it. If you think about it, it's really the matrix 4 minus 2, 1, 1 minus, I can think of this way, lambda 0, 0, lambda, which is our matrix that we started with, minus lambda times the identity. So this is actually written as A minus lambda I. If you looked at any textbooks or anything, this is actually the matrix that people end up caring about, that we end up caring about, A minus lambda I. That's the matrix we want to be not invertible. And so if A minus I is not invertible, its determinant must be 0. That's what we've seen now about square matrices, or just about matrices being invertible. we can sort of get rid of all the vector considerations and just say there's this number we associate with the matrix. That number is called the determinant, and we want that number to be 0. Then the determinant of A minus lambda I equals 0. But the determinant of A minus lambda I, if we just look at A for a second, let's just look at this. That's going to be true in general for finding eigenvalues, but I'm just trying to think about this example. 4 minus lambda. It's the AD minus BC thing, right? Do an AD minus BC negative 2 times 1. And we want that to equal 0, but let's write this out. This is actually, we could actually FOIL this out, right? And this, well, okay, so we get 4 minus 5 lambda plus lambda squared, and then minus 2 is plus 2. So this is actually lambda squared minus 5 lambda plus 6. And we're setting that equal to 0. And that's a quadratic. Again, you have to stop and think. This is kind of lovely because we've gotten rid of x1 and x2. We're not worried about those right now. We're just trying to find lambda. That's the thing that's a little bit counterintuitive about the subject is that you actually find the eigenvalues first and then find the eigenvectors, whereas it feels like the eigenvectors should be the thing you find first. But let's go back to this example. This quadratic factors lambda minus 2 times lambda minus 3 equals 0, which implies lambda equals 2 or lambda equals 3. Lambdas are looking weirder. Lambda equals 3. And if you go all the way back to the beginning, oh, look. 2 and 3 were our numbers that we multiplied by. So we've actually found and identified the eigenvalues. These are the eigenvalues. Okay, lambda equals 2, lambda equals 3 are the eigenvalues. So we found those, and those are less mysterious now. Okay, but now how do I find the eigenvectors for eigenvalue 2, for example? Well, now we just want to go back up to this matrix up here, this one again, and plug in a lambda value and actually see that and actually find the homogeneous solutions, right? And we could go all the way back to here, but that would be, or no, we could go all the way back to here, but that would be a little counterproductive because we would just end up subtracting over anyways and finding the homogeneous solutions. So let's just do this. So for lambda equals 2, so we plug back in to a minus lambda I. So that's a minus 2i, and that's really just subtracting 2's off the diagonal of our original matrix. So that's 4 minus 2, negative 2, 1, 1 minus 2. And that is 2, negative 2, 1, negative 1. And that should jump out to you that this now is a matrix that clearly the columns are not linearly independent, right? Which means that this is going to row reduce nicely. So, and we want to find the homogeneous solutions. So if we took the augmented matrix 2, 1, minus 2, minus 1, we augment 0, 0, now we actually, this actually row reduces almost instantly to something like this, which implies x1 minus x2 equals 0, or x1 equals x2. So x1, x2 is really just, so x2 is the free variable, so it's x2, x2, which is x2 times 1, 1. So 1, 1 is an eigenvector, so with eigenvalue 2. We actually use 10, 10, but notice we can scale this, right? So 10, 10 works just as well, which was what we found. That was our vector I called V. I used 1, 1 just because that's the simplest one, but 10, 10 worked for the population modeling better. So that's how we found that. So that's V. So that's kind of cool. We've actually recovered V, the eigenvector V, with eigenvalue 2. And just to finish this off, just to see how this works, just to make sure we're going to find W, when we try 3, we're going to look at A minus 3i. So I'm going to subtract 3 off the diagonals of our original matrix A. And again, we should get something that looks sort of degenerate. Oh, this, I see what's going on. That was not, sorry, this was a +1 right there. I knew something was going wrong because I wasn't getting the matrix I wanted. So -2. And again, this also is a matrix that's very clearly not, it has non-trivial homogeneous solutions, that the columns or rows are not linearly dependent, that, you know, it's going to have just one pivot. And so when we row reduce this, well, that's kind of silly. It's just, we just get the first row. And that means x1 minus 2x2 equals 0, or x1 equals 2x2. And so x, the solution to this is 2x2, x2, if I rewrite it in terms of the free variable, times 2, 1. So this is the eigenvector with eigenvalue 3. Eigenvalue 3. And remember, W was 2010. So that's also a nice multiple of 2, 1. So I really reverse engineered the predator-prey problem to work out very nicely. I picked 3020 as my initial population just so that it would actually exactly work as the sum of the two eigenvectors. And so that's how we found our eigenvectors and eigenvalues. And that's the process. I mean, once you find the eigenvalues, this is definitely the process. Finding the eigenvalues is just really taking the determinant of A minus lambda I. So I'll go through this. I just want to do this exploratory example where we see how it happens. But in general, this is how it's going to work. And I'll make some more videos showing the general case and illustrating with more examples. Okay, I'll stop there.